Okay, let's work through, if we can get over here. Come here, chicken. I just want to come over here. All right, let's look at this problem. Jet flying at 134.1 meters per second along a straight line that makes a turn along a circular path. So it's basically about to go around a circle. Meow. All right, of some unknown radius, and we want the acceleration to produce a feeling of 1 gravity on the pilot. Oh, well, this is an unnecessarily easy problem given everything I just talked about. So we know that our v squared over r is going to be that acceleration. Now, it's saying the feeling of acceleration, that's the actual acceleration. I'm trying to teach you real stuff here on top of you just, getting the grade and moving on. All right, so 134.1. You know what? I'm going to do dimensional analysis because I feel like you need to learn something. Squared over a radius equals 9.81 meters per second squared. So I've got 134.1 squared is, come on, chicken, go. All right, 17,892, 17,982 meters squared over seconds squared equals 9.81 meters over seconds squared times r. So r, I'm just doing an unnecessary amount of work right now. I know you already have the answer. 17,982 meters squared over seconds squared over 9.81 meters over seconds squared. So look what happens. The seconds squareds cancel out. The meters squared over meters just ends up with meters on the top. So we end up with just meters. Look, you get a radius in meters. Who would have thought that would have happened except for anybody who trusts equations without thinking? But, it's still good to know that even if you don't blindly accept it, why can't I hit a button there? There we go. All right, so we get an 1833. So R equals 1833 meters. Yay! All right. So, that's just kind of a little thing to get you introduced to the concept of what we're doing here. But really what's going on is infinitely more powerful. And honestly, to do this for real, you need to get into polar coordinates. There's so much more to do with this. So this is in centripetal acceleration. Okay, equations of motion. Okay, so they're introducing here to you another, why they call it angular frequency. All right, they're calling something else, basically, omega. They're going to call it angular frequency. I'm not going to call it that. I'm going to call it angular velocity, which is basically how fast is something rotating. So if you think about revs per minute, like if you have you can't say like a record player, what still rotates? I mean, I don't know. What are things hold on, I have to do this. There you go. Examples of everyday items with angular velocity. A car wheel, I should have thought of that. A car wheel spins if it's going the same speed. If a car wheel is just running, it has an angular velocity. A ceiling fan has an angular velocity. A fidget spinner, record player. Electric toothbrush head. Okay. Well, there you go. This muscle. I like the idea of the things that are like solid. So let's go with a ceiling fan. I like the idea of a ceiling fan. So if your ceiling fan rotates, a certain number of revolutions per minute, that would be its angular velocity. Fun fact, if it goes a certain theta, my fan blade rotated 10 degrees, then that's its basically its displacement. And I think we actually call it angular displacement. I don't think your book's going to get into this, but it might help you understand what's going on. But omega is the angular velocity, which is actually d theta dt. So it's how fast is the angle changing. You can also get into angular acceleration, which is d omega dt. Not sure if we're getting into that. But these are listed here as your sine and your cosine, and that is assuming for the purposes of this whatever it is that you've got going on, that you're measuring everything from a standard place. So I guess what I'm saying is your book is oversimplifying it, but the cosine goes with the x component and the y, or the sine goes with the y component, because it has to do with you getting, and in fact, why is it saying that? Oh, I get what it's doing. Okay. So it's calling this your angular frequency, because frequency times time. So think about it. Okay, I'm going to look at this equation. This is actually really kind of interesting. So if I'm looking at this equation going, what does this equation mean? Okay. So it's saying the position is cosine omega t times blah, blah, blah. Okay, well, if I know omega is done in something like revolutions, hold on, like revolutions or theta or, something like that. Let's just say it's the number of thetas per minute, right? Omega is theta per minute, and then time is measured in minutes. Then the minutes cancel out, and so that's really just a cosine theta. And this would be a sine theta. So remember, we've always done, if we measure from the positive x-axis going positively, that the x component is cosine and the y component is sine theta. So the reason that this isn't saying theta is because it's saying omega t. So if you do omega times time, you get position, just like if you do velocity times time, right? You get position. Remember that equation? X naught plus vt equals x. Well, there's similarly an equation that says theta is equal to omega t plus the initial theta. Okay, so that's where these equations are coming from. So they're kind of hand-waving it. So I don't know if explaining it to you makes it make more sense or less sense. So the omega t is coming out of the idea that if you multiply rotational velocity times time, then you just end up with position again, so you can go ahead and you can take the sine and cosine of it. And then this is the period, is the period of motion, so the time to take one revolution. So in whenever, I'm not going to say when we measure stuff, because a lot of times when we measure stuff in degrees, but when we do math, a lot of times we'll end up doing math in radians, and so that's why it's 2 pi. So we do 2 pi revolutions in 30 seconds, then that's the angular velocity. So just however you kind of want to do it. So if I said revolutions per minute, however you want to do this. So basically another way to say this, so, I go through 2 revolutions per minute, right? Because 30 seconds is 1 minute. So another way to write that would be 2 revs per minute. I feel like I talked backwards into that, but maybe it makes sense. So if you have a period of t, that means every 30 seconds, if you have a period of 30 seconds, that means every 30 seconds you go 30 seconds here, 30 seconds here, 30 seconds here, 30 seconds here. You're going 2 pi radians every 30 seconds. So you could also say, well, I'm going 4 pi radians every minute. So a lot of times you'll hear it described as like revolutions per minute, but the period itself is 30 seconds because it only takes 30 seconds to go around once. So this is more of a, what do you want to call it, a vocabulary lesson.